BC Calc, this is your day 24 notes on a quick summary of curve sketching. And we're going to add to our process with some more tests today that will help us to determine maxes and mins. And you might like these tests better than the ones we currently have. So before we get started today, the entire front page is just kind of a recap of some things that we should know at this point. And I want you to take just a minute or two, hit pause, and see if you can fill in what do we know about making an accurate sketch of a curve from last year in PCH. What are some of the things that you can identify that would help to make our sketch as accurate as possible? And then what are some of the things that we've now learned in BC Calc this year that will help us just to even make our sketches that much more complete and accurate? So like I said, hit pause because I'm going to go through my list here in just a second, see how many things you can list in each of those columns. So if you're ready, here's what I have in column 1, what you should know from PCH. And there's probably some other things you may have listed, so you can let me know that next time I see you in class. We should be able to identify, maybe some domain and range, if there's any restrictions that apply there. Certainly the intercepts we'd want to be able to find to accurately sketch the function. The symmetry, if any exists, that's kind of helpful sometimes in terms of thinking about, is there y-axis symmetry, origin symmetry that might help to determine my final sketch. And then certainly asymptotes where applicable. We should be fairly comfortable about finding vertical asymptotes, horizontal asymptotes, and even slant asymptotes where they apply. What do we now know in BC Calc? Here's a quick list of things. Well, this is something you probably could have put in PCH as well. You talked about discontinuities last year. All right, so knowing where certain functions are discontinuous, and maybe that even plays a hand in talking about asymptotes in certain instances. Points where a graph is non-differentiable. So that's something that we've discussed, as far as if we have kind of these sharp, ouchy corners on the graph, or, discontinuities are definitely places where the graph is non-differentiable. We know how to algebraically determine increasing versus decreasing according to the first derivative test. So that's good to add on to our list. We now know how to determine points of inflection. So if we find the second derivative and we see that sign change in our f double prime number line, we know that that represents a point of inflection. And of course, we know a little bit more about concavity with the second derivative. Relative extrema would be connected to the first derivative test, but we'll see how the second derivative can also help us to identify relative extrema. So if you thought of something really good here that I've seemed to have missed in my list, then certainly let me know next time I see you in class. I'll touch base with you guys and see if there's something critical that you think I've left off the list here, but it seems pretty complete to me. So when we say create a sketch, it's not just, any old curve that we're going to, throw onto a graph. We want you to consider all of these things when making your sketch as accurate as possible. We can find very specific locations where these things are happening. So continuing the recap here, we have these quick notes about f of x and f prime of x, what happens if they're increasing and decreasing. So if the original function f of x is increasing, what we would expect to find is that the derivative is positive. Right? If you think about the slopes of all those tangent lines on this increasing curve, we know that those slopes are all positive. So that helps me to confirm increasing and decreasing. So on the other hand, if the original function is decreasing, we know that the derivative is negative. And this is going to help when we start putting things together where maybe I'll give you the graph of the derivative and you have to tell me some things about the original function. So we'll eventually kind of work forwards and backwards with these ideas. If the derivative is increasing, we know that the second derivative has to be positive, which means that the graph is concave up. Right? If the first derivative goes from negative to 0 to positive and it's increasing in that form, the second derivative, the slopes there are positive and greater than 0. And finally, if the first derivative is decreasing, that means the second derivative is negative. So what that means is that we would have something that's concave down. Okay, so a good quick summary there. And then at the very bottom, we have inflection points as a quick summary from the prior lesson. Inflection points occur when concavity changes. If we switch from concave up to down or vice versa, we get a point of inflection. When does this happen? It happens in 2 instances. It happens when the second derivative is equal to 0, or when the second derivative does not exist. So those are points that we're going to wind up putting on a kind of f double prime number line and checking to see if we have a change in sign. And if we have a change in sign at any of those critical points, then we would assign an inflection point, or certainly at least a change in concavity at that location. Okay. So this is a great summary of everything we've talked about so far in terms of curve sketching. Let's kind of extend that a little bit. And if you look at the next page, we're going to take a look at finding algebraically the coordinates for the point of inflection for the cube root of x. Now, I think if you know what cube root of x looks like, you're going to be able to find the point of inflection without even necessarily doing the calculus, but let's use calculus to confirm it. So if we start with f of x equals the cube root of x, which is x to the 1/3, if you want to use some power rule here, the first derivative would be 1/3 x to the negative 2/3. And then the second derivative, which we need to figure out point of inflection, right? Let's see if the concavity changes. The second derivative would be, in this case, negative 2/9 x to the, subtract 1 up there, negative 5/3. So negative 2/9 x to the negative 5/3. Which, if you want to rewrite that using a positive exponent, this would equal negative 2 over 9 times x to the 5/3, which is the same thing as the cube root of x to the 5th. If you want to go back to some cube root notation there. So what we have to ask ourselves is, well, if we're trying to find points of inflection, it's where the second derivative equals 0 or where the second derivative does not exist. And what we'll find is if you set this equal to 0, there's no solution there. So we're not going to get a point of inflection based on finding where this equals 0. But if we think about where the second derivative does not exist, f double prime does not exist at x equals 0. So if we go ahead and put that on an f double prime number line, f double prime, we're going to test some values and see what makes this positive, what makes it negative. So if I test something like negative 1, the cube root of negative 1 to the 5th is a negative number, and a negative divided by a negative altogether here is positive. So what does that tell me as far as an f double prime number line goes? This is not about the original function increasing or decreasing anymore. It tells you that the original is concave up. Let's go over to the right side. If I test positive 1, the cube root of 1 to the 5th is a positive number. Negative over positive altogether is negative. So then to the right of 0, we have to switch over to concave down. And the conclusion is that at x equals 0, we have a point of inflection. All right, so if we have a point of inflection there, let's just confirm graphically that that is true. It would happen at the point 0, 0 if you plug it into the original. Yeah, we know what cube root of x looks like. It's the walk like an Egyptian function. I've probably never said that before. I'll show you my walk like an Egyptian dance next time I see you. All right, so it's the function that is, yeah, look at it. It's concave up, shaped like a cup, until I reach 0, 0. Then it switches over to concave down. Okay, so for more complicated functions that maybe we don't know exactly what they look like, this will be a good test. The second derivative test helps to confirm that we're going to wind up having a point of inflection there. All right, does y double prime equaling 0 always give you a point of inflection? Is that always going to be the case? Well, if we do the second derivative test, what we have to confirm is at that value, do we see a sign change? Okay, because if there's no sign change, it's definitely not a change in concavity, and it's not a point of inflection. Let's think about maybe, again, we probably know what these two things look like, but let's just see the calculus behind them and how we can analyze what's going on at some of these critical points. So for y equals x to the 4th, we know that y prime is equal to 4x cubed. So the critical point here is when, if I set this equal to 0, is that x equals 0. Okay, so if you put 0 on a number line, this is your y prime number line. Testing a negative would output a negative. Testing a positive would output a positive. So we're going from, in this case, decreasing to increasing, which means that we have a local min at x equals 0. I'm not going to show the justification for now, but we know we would justify by saying the derivative is negative to the left of 0, positive to the right of 0, which indicates a local min. All right, what would the second derivative be? The second derivative would be, in this case, 12x squared. Okay. So if I set that equal to 0, the critical point here would also be at 0. So here's my y double prime number line. And again, does setting this equal to 0, does this guarantee that this is a point of inflection? That was the question. Is this going to be an inflection point? Well, if I test something to the left of 0 and the function 12x squared, we're going from positive to positive. We're going from concave up to concave up, which means no point of inflection here. Okay, we got to see a change in concavity for that to happen. And of course, we know it's not a point of inflection because this graph is always concave up. Y equals x to the fourth. We have a local min at x equals 0, but the actual graph of f of x looks like that. Okay. So no surprises there, but guaranteeing when you set this equal to 0 and you do your y double prime number line test, it doesn't guarantee that at those critical points we'll have that change in signs. So just be cautious about that. We can't operate under that assumption. All right, and for something like y equals 6x cubed, let's go ahead and find the first derivative. So y prime would equal, in this case, 18x squared. So if I set that equal to 0, we get 0 as the critical value. So if I test something to the left of 0 and to the right of 0 in the function 18x squared, that's an always positive function. So for the same reason, critical points don't always indicate local extrema, do they? This is going from increasing to increasing. So it's increasing over its entire domain. There's no local extrema that we're finding at x equals 0. So it's not a max-min point. However, if I find the second derivative, that tells me a little bit more of the function. So y double prime is 36x, which if we set that equal to 0 on the y double prime number line, we're partitioning around 0 again, lots of zeros to partition around. To the left of 0, we're negative. To the right of 0, we're positive. So we're going from something that's concave down to concave up. So therefore, x equals 0 is a point of inflection. And since we know what the graph of 6x cubed looks like, we can certainly confirm that as I sketch 6x cubed, you're going from concave down, and then as soon as you hit x equals 0, it turns and switches over to concave up. So knowing something about these curves, of course, we know those locations, but for, again, things that get more complicated for us, this is what we're looking at for our two tests. Our first derivative test and our second derivative test, how we can confirm local extrema versus what we're seeing if we determine a point of inflection. All right, so if you have any questions about that, we'll touch base on that in class. If we move over to the next example, I kind of like this one. This is not necessarily a graph that we would commonly know what the sketch of it looks like, y equals x plus sine x, but using our knowledge of critical points, inflection points, increasing, decreasing, we can actually pretty nicely make an accurate sketch of what this graph looks like over the interval from 0 to 2 pi. So let's start, if we're going to find some critical points, by finding the derivative of x plus sine x. So the first derivative, y prime, would equal 1 plus cosine x. So we're going to set that equal to 0. And we're going to solve this over the interval from 0 to 2 pi, see what values satisfy, in this case, cos x equaling -1. So cos x equals -1 only at one value on this interval from 0 to 2 pi. It's only at x equals pi. So when I go to make my y prime number line, I'm going to only have to partition around pi, but I think it's also, since we're graphing this over this restricted interval, to put 0 and 2 pi on the number line so that we can see what's happening over this interval, but certainly surrounding that critical point at pi. So let's see, if I test something like pi over 2, cosine of pi over 2 is 0, plus 1 is positive. If I test something like, how about 3 pi over 2? Oh wait, cosine of 3 pi over 2 is also 0, plus 1 is positive. So at x equals pi, do we have a local max? Do we have a local min? Well, it turns out to be neither of the two. But what I do know from my first derivative test here is that this graph is increasing over the interval from 0 to 2 pi. So when I go to make my sketch, that will be an important thing to consider, that it is always increasing over this domain. All right, so we need a little bit more potentially. We probably would want to figure out what the second derivative test tells us. So the derivative of 1 plus cos x, well, the derivative of a constant is 0, but the derivative of cos is negative sine x. And if we think about where negative sine x is equal to 0, this would happen at 0, pi, 2 pi, things like that. All right, so the critical point here is really just going to be figuring out what's happening surrounding pi again, since 0 and 2 pi are the endpoints of the interval anyway. Okay. For your y double prime number line here, if I test pi over 2, sine of pi over 2 is 1, but then negate it, so that's negative in this region, so the graph is concave down. If I test 3 pi over 2, sine of 3 pi over 2 is negative 1. Oh, negating negative 1 makes it positive. So now we find that the graph is concave up from pi to 2 pi. So we need something that's constantly increasing over this interval and switching from concave down over to concave up. Can you picture it? Think about what we just sketched for 6x cubed, right? That was increasing over its interval, and it went from concave down to concave up. So it's a fairly similar looking sketch. Maybe you'd want just a couple last minute things, like if you went to the original function, kind of figuring out the y values of these key points along the way. So f of 0 would be 0 plus sine of 0. That's just actually still 0. F of pi is going to be pi, and f of 2 pi is going to be one of being 2 pi there. So if you just want some points that we can use as kind of reference points here, when I go to make my sketch, we know we have 0, 0. We know we have pi, pi, 2 pi, 2 pi. But certainly it's not a linear function that connects those. We have to sketch something that's concave down and switching over to concave up and constantly increasing. So when you sketch this graph, start concave down shaped like a frown, but then at x equals pi, we have a point of inflection, and then we switch over to concave up. And if you were to check this on your calculator right now, this is fairly accurate to what we would see over the domain 0 to 2 pi. So I like this because it's something that, based on what you learned last year, you probably wouldn't have gotten the accuracy that we needed for the inflection that contains these points, right? Without a calculator, we wouldn't have been able to use the calculus to determine where the concavity changes. Okay, sounds kind of cool. Let's look at this one, and I'm going to have you think about this before I see you again. Now, one quick note about this is I want you to make a sketch of a possible graph of f of x. There is not one unique graph that you would come up with here. But I do want you to think about this initial condition. F of 0 has to equal 2. That's going to be in common on all of our graphs. And notice how this equation right here is not the original function f of x. This is the second derivative of f of x. So make your f double prime number line here with those critical values from this equation above. Do some partitioning and see if you can use that partitioning and what the f double prime number line tells you to make a possible sketch of the original f of x. Okay, go ahead and try that before I see you next. Maybe use a pencil in case you're way off and we need to fix it. But I have a feeling, based on what we've seen so far as what the second derivative test tells us, that you guys can come up with something that makes sense there. All right, lots of summarizing today. Here's a quick summary of what we know about extrema from the first derivative test. Right, we hopefully are pretty good that if we're less than 0 to the left and greater than 0 to the right, then we have a min. And if that switches around, we get a max at x equals c. All right, second derivative test. This is going to be something that's a little bit new, but for the second derivative test, if we have a critical point such that the derivative equals 0, and if we plug that into the second derivative and find it's negative, what does that mean? It means that it's concave down. So that's another way to justify a relative max. If we find the first derivative, set it to 0, and get a critical point, plugging that critical point into the second derivative and seeing where it's negative versus positive, that's justifying extrema. Now, the only issue is that if you plug it into the second derivative and it equals 0, we can't tell concave up versus concave down. So you'd have to go based on the first derivative test. But if you have a critical point where the derivative equals 0, plug it into the second derivative and it's positive, then we know that it's concave up, and concave up graphs have a relative min at that location. So it's kind of nice that we have this as an additional test. And I'll talk about, when it might be beneficial to use the second derivative test, maybe as opposed to the first derivative test. Okay, so talking about, where extrema exists, it exists where the derivative equals 0 or where the derivative does not exist. One quick note, though, is that's for an open interval. If you're looking at extrema on a closed interval, then the max min values are where the derivative is 0, does not exist, and at the endpoints. So what we're going to find is if we have a closed interval and we're looking for extrema, we're going to go ahead and test the endpoints of that closed interval to see if maybe those represent absolute max or min locations. So here's an example of that. And by the way, page 260 has a lot more definitions of extrema if you need anything there. But this says find the absolute max and min of f of x equals x squared plus 2x plus 1 over the interval from -2 to +2. So let's use our first derivative test. So f prime of x would equal 2x plus 2. And if I set that equal to 0 and solve, we'll very quickly get that x equals -1. Okay. So x equals -1. If I do my test and test, let's say -2, 2 times -2 plus 2 is a negative number. If I test 0, we get a positive number. So we see this is decreasing to increasing. And therefore, we have some sort of min at x equals -1 from decreasing over to increasing. But is it the absolute min over this interval from -2 to 2? It's definitely some sort of minimum. Does it happen to be the absolute min? Well, what we're going to do is we're going to go ahead and not only test the y value in x equals -1, but we have to test the endpoints of this interval too. Maybe those represent absolute max and min values. So we're going to do f of -2, f of the critical point -1, and then f of +2, and see what those corresponding outputs are. So you do f of -2, you're going to get 4 minus 4 plus 1, so that's 1. F of -1 would be 1 minus 2 plus 1, which is 0. And then finally, f of 2 would be 4 plus 4 plus 1, which is 9. Okay. So over this interval, from -2 to 2, it turns out that x equals -1 is the absolute min. Okay. So the absolute min occurs at x equals -1, but when we say what's the absolute max or the absolute min, it actually represents these outputs. So even though the min occurs at x equals -1, the absolute min for f of x is 0. Okay, we're talking about the y value that's associated with x equals -1. And therefore, over this interval, the absolute max for f of x on the interval -2 to 2 is 9. Of course, on an open interval, over its entire domain, let's say this doesn't have an absolute max. But if we're looking at it over a closed interval, we can define the absolute max as being at one of those endpoints. And the absolute maximum this takes on from -2 to 2 is a value of 9. So just knowing how to answer the question, we wouldn't say the absolute max is 2. The absolute max occurs when x equals 2, but the actual function value there is 9. So just make sure we're kind of consistent and okay with that. All right, so we're going to do one more thing together, and it's not this example. I want you to make sure you've tried this before you see me next, given this function. find and justify any relative extrema. So that's going to be your first and second derivative tests. Probably the first derivative test is what you'll want to use for that one. But I want to do this last one. It says find the maximum profit for P of x equals 4x minus 500 minus 0.001 x squared. Okay, and it makes sense that we're only considering this for values of x that are positive. So to find the maximum profit here, now that we know all we know about extrema, we can find the first derivative, p prime of x. And that's going to be, in this case, according to the quadratic piece at the end, negative 0.002x, and then plus 4. So if we set that equal to 0 and solve for x, dividing over the negative 1 over 500 or 2 thousandths there, you wind up getting x equals 2,000. Okay, so 2,000 is not the max profit. The value of x equaling 2,000 may wind up maximizing the profit. Why do I say may wind up maximizing? Well, we really should do the first derivative test to confirm that. So if I do a p prime number line here, we're going to put 2,000 on the number line. We're going to test something to the left and test something to the right. Let's see what happens. So if you test something like 1,000, you're going to wind up getting something in total that's positive. And then if you test something like 3,000, you get a negative. So when we go from increasing to decreasing, we know that that represents a local max. Okay. So we would justify that, right? Since f prime is changing from it's greater than 0 to the left and less than 0 to the right of 2,000, we know that there's a max at that location. Okay. Or what else could I do? So this is how the first derivative tests, and we would write that justification. What if I also find the second derivative? Pretty easy to find in this case, right? Isn't the second derivative just negative 0.002? So what's the conclusion if the second derivative is always negative? Well, since p double prime of x is always negative, the conclusion is that p of x is concave down. Which means that x equals 2,000 is a local max. Okay. So remember that second derivative test, if we find the second derivative is negative, which it always is negative, then the critical point from the first derivative test, that x equals 2,000, has to be a local max. Okay. Because negative second derivatives means that we're just concave down, and then that critical point has to be located at a local max. So this is another way to justify. And this kind of can be a nice quick justification if you don't always love writing the list, greater than 0, less than 0 to the right of your critical point there. But really quickly again, what is the max profit? The max profit is whatever P of 2,000 is. And P of 2,000, if you plug that into the function here, is $3,500. I guess we're talking about profit here. Okay. So make sure you actually, again, answer the question. The max profit is not x equals 2,000. It occurs at x equals 2,000. But the max profit's 3,500. Okay, that's it from me for day 24. Make sure you go back and try some of those questions. I think I just left maybe 2 for you to think about on your own there, and we'll go over them next time I see you. Have a great day.